This is the Earth Science Classroom. Welcome back to the channel. This video is on the scientific method, what it is, and the origins of this revolutionary way of analyzing natural philosophy, natural phenomena, and how these amazing pioneer scientists revolutionized how humans perceive nature, figure out nature, and formulate theories and laws about nature and everything around us. So what is the scientific method? So it is a step-by-step guide or process of what you should do if you're conducting a science experiment or you're trying to find out something new about what's around you, nature or the origins of the universe, or as simple as how does something fly in nature, or how does something work or function, whether it's inside the body as a doctor or outside as a biologist, or as a chemist, or as a physicist, or in this case as a earth scientist or a geoscientist, and figure out how the earth works. The scientific method is 5 main steps, and it's basically the process of how scientific knowledge is obtained. And it's a systematic method in which to collect, analyze, and interpret our natural world. And also it can be the use of empirical data, so numbers and observations and factual information to take as a uniform method of processing information. So what it is, if someone from across the world in, let's say, New Zealand or the Philippines or in South America, the experiment can be done on something, and those results, those comprehensive step-by-step guide of how to complete this experiment and how to get to these conclusions on this data you collected, that can be used and interpreted or understood anywhere around the world in different languages, because the method, the step-by-step method, is standardized. It is the same. It is uniform. So in America or in Europe, we don't do things differently than to, say, in China or Japan or Ghana. It's all going to be standardized, so scientists have a platform from which to work on. Now, the origins came in the 17th century, so as the years of 1601 up to the beginning of the 18th century, around 1726 to 1735, where certain scientists underwent what's called the scientific revolution, and they started to look at our natural world in a different perspective, a different way than previously understood. Now, the previously understood ideas and concepts really formulated from the church and from religious texts like the Quran or the Bible or the Torah. And those kind of influenced how humans perceived our world and how things work. And it was done basically on, let's say, even magic, and how things appeared based on belief systems and perpetuated superstitions, and basically on the verbal word of mouth only, without real conclusive evidence or data or numbers or words to really back it up. It was just word of mouth based on people's perceptions of and inferences of nature. Now, in came the revolution, the pioneers of this new way of thinking, this new order of science and math and calculus and engineering and calculating how our world works in more detail. So first was really Copernicus, the Polish monk and astronomer, who basically went against the church and said that the sun was in the center of our known solar system, and it wasn't the Earth, and it was the heliocentric model. Brahe and Galileo followed along with their own additions to how to obtain information, how to conduct a scientific experiment in the terms of what science was in this new revolution, was the use of equipment, the use of math, the use of numbers and calculus and algebra and geometry, the use of words to explain, and the use of a standardized set of an order of steps you must take to get to these conclusions to make it, let's say, scientific. So Brahe and Galileo, again, Galileo really pushed the essence of how to do an experiment, how to work on obtaining information and gathering data. And Galileo's work was mostly around 1609. Then we had people like Sir Francis Bacon, who was a lawyer first, and then went into more of a science and more philosophy, and looked into applying forensic methods into obtaining scientific data and also using logic. Now, logic is using reasoning to produce valid points that make sense of what you're doing. So that was Bacon's contribution to the scientific method. Then was Kepler, who used mathematical equations and formula to figure out the movement of stars and motion of planets, which again was in addition to Brahe's observations in astronomy using a telescope, and also Galileo's. Then we had Bernoulli, which he added various principles based on this method of obtaining information. And we also had, in 1637, we had Descartes, who applied, again, more math, like with Newton and with Kepler. He also added deductive reasoning and some skepticism into the field of acquiring information scientifically. So to basically question and review and really critique what you're doing as you're doing the experiment, which can lead to, again, trial and error and lead to more refinement of your craft. So what does it look like? Well, there's 5 components, as I stated earlier, and these 5 components must be incorporated, so all 5 must be present in the process of acquiring information. Now, this is to do with producing paradigms and models and patterns within the natural world to look at theories and laws which go about looking at everything is working to a certain function. Everything works together, and if one thing is correct about it, then the other thing is correct, which again is using reasoning and logic. Isaac Newton using the 4 rules of reasoning, using it scientifically, and the 4 rules about basically explaining what happens using only science and other things that we come into it. The paradigm is producing models and patterns and looking at the same behavior. The result of one would apply to others. So let's say with Hutton, with the geologic history, that if a rock is made a certain way, then in the future, in the past, those rocks will also be made the same way. So that's the uniformitarianism principle of geology coming in. And then the 4th law would be that, like in all good science process, is the conclusions or understanding of that experiment can be obsolete or rewritten or improved in the future if more knowledge is acquired about that subject and the initial conclusion is inaccurate or incorrect. Like 200 years ago, 300 years ago, we thought the Earth was flat. Now we know different. So the 5 parts is, first you have a problem, you have a question. You are asking you something about what happens, or you see something happening, or why is it going to rain later? Why is the tide so low? Why does the Earth spin? Why is the sky blue? Why is this ocean full of animals? Anything. State a problem, have a question. Then you have a hypothesis. You are thinking the reason why. Okay, well, I think this or I think that, and you're trying to understand it. Then you're going to base your experiment or design experiment, number 3, on your hypothesis, which is based on your problem or your question. So 1, 2, and 3 are a step-by-step way to get to the point. Then after the experiment has been conducted, you're going to have data. You're going to have quantitative data in different ways, and you're going to analyze and pick apart that data to figure out what's going on, what's the data telling you from the experiment, and then from that analysis of your data, both numbers or words, you're going to draw conclusions and produce theories or even laws. Now, a law would be something that is always going to happen, the same conclusions, the same thing happens. That's a law. A theory is something that they think happens, but they're not completely sure it's concrete and always happens, so it's a theory. So these conclusions are drawn, and that would help to aid the knowledge of humans about our planet. So each experiment is going to develop and add more knowledge to us about our natural world and our place within the universe.